Welcome to this lecture. This is the final lecture of week 5. In this week, we have discussed about series of independent random variables and their almost sure convergences. In particular, we have seen the 2 and 3 series theorem talking about certain conditions involving the almost sure convergence. We then focused our attention to the law of large numbers and the characteristic functions. In particular, involving characteristic functions, what we saw is that characteristic functions uniquely identify the underlying probability measure. In this lecture, we are going to see certain exercises and problems based on the content that we have covered in week 5. So, without further delay, let us continue the discussion using the notes. Alright. So, again we are going to continue writing omega f p to denote some arbitrary, but fixed probability space. So, let us start with the discussion with exercise 2. So, here we are given that for some constant c positive, so this series converges. So, the idea here is that we are first of all looking at the events where mod of x n exceeds that number c, and we are looking at the probabilities of this event. Finally, we are looking at the sum of these probabilities and we are asking that this series should converge. Now, here you note that by definition we are truncating our random variables at c in this sense that if mod of x n is less or equal to c, then we will take the original value of the random variable, otherwise we will set it to be 0. Now, here as long as we are looking at these events where modulus of x n exceeds c, so in that event we are immediately having the fact that x n does not match with its truncation. So, as long as modulus of x n is strictly greater than c, then the truncation takes the value 0. However, the modulus of x n is strictly greater than c and therefore, they do not match, and this is if and only if condition. So, we are just rewriting this event that modulus of x n is greater than c, it is exactly the event where x n does not match with its own truncation. And therefore, by the given condition that we are working with, we can appeal to the Borel-Cantillo lemma first half. So, remember this result we have discussed in theorem 9 of week 1. So, here what we are giving is that since the series of events has the property that the corresponding sum of the probabilities converge, then here the lim sup of the same events must also have the probability 0. So, this is application of the Borel-Cantillo lemma first half. However, this limit superior of these events has this again alternative description that the events modulus of x n greater than c happens infinitely often. So, this is the same description of the limit superior of these events. However, as we have just pointed out, the event x n greater than c is equivalent to the event that x n does not match with its own truncation. So, therefore, we are saying that the probability of the events that x n does not match with its own truncation infinitely often, that must also happen with probability 0. Now, here we just rewrite it back in terms of the limit superior of these same events, that we are now looking at limit superior of x n does not match with its own truncation. So, that event has probability again 0. So, this is just the identification that we are talking about through the Borel-Cantillo lemma, and that was the exercise that was left out for you. Alright. So, this is just an application of the Borel-Cantillo lemma in relation to the convergence involving almost sure convergence of series of independent random variables. Now, here we again look at a similar type of a problem that was given in exercise 4 part 1. So, here we are dealing with equivalent sequences. Remember what are equivalent sequences of random variables? So, we are having two sequences, one x n, another y n. Now, we are going to say that these two sequences of random variables are equivalent in the sense that the probability of the events x n does not match with y n. If you consider the series involving that, that series should be convergent. Now, here if that again happens, then we just rewrite the corresponding events where x n does not match with y n in a different sense. So, we will say that x n does not match with y n, that is equivalent to the fact that x n minus y n is not equal to 0. So, this is just rewriting the same event in a different form. So, therefore, their probabilities also are the same, and now we again appeal to the Borel-Cantillo lemma first half and go to the limit superior of this sequence of events. And we will say that the limit superior of x n minus y n not equal to 0, those events have probability 0. Now, rewriting in terms of the infinitely often description of the limit superior, we end up with this fact that the probability of such an event is again 0. Alright. So, now we are going to appeal to another type of an argument we have seen in week 1. So, there in lemma 1 of week 1, by looking at certain sets of probability 0, we were able to establish certain kind of pointwise convergences. Now, here also we are going to look at a similar type of an argument, and let us look at the complement of this measure 0 set that we have just obtained by the Borel-Cantillo lemma first half. So, take any point from the complement of this set, then there exists some positive integer capital N may depend on the point that we have chosen, such that after a certain stage we must have x n minus y n to be 0. So, now remember, in the limit superior description what we have is that x n minus y n not equal to 0 happens infinitely often. So, therefore, the complementation will give you that x n minus y n is not equal to 0, that can happen only finitely many times. So, therefore, depending on your choice of small omega, after certain stage you must have x n minus y n equal to 0. So, now since we are interested in the pointwise convergences of this kind of a series, and after a certain stage all the terms inside the series are actually 0, therefore, we immediately have that the series must converge, and consequently using the fact that this probability of this limit superior of events is 0, and on the complement we have established the convergence. Together with these two facts, we conclude that we are having the almost sure convergence of the sequence of random variables x n minus y n, then goes from 1 to infinity. So, here is the idea that we are having now almost sure convergences for the equivalent sequences when we are looking at the differences of them. So, this was again an application of the Borel-Cantillo lemma, and we have simply used a familiar argument that we have discussed earlier. So, let us now move on and discuss another exercise. So, here we go to exercise 7. In the exercise 7, we are asked to construct some specific type of random variables y and z with certain interesting properties. So, here we recall some results first and then come back to exercise 7. First, we recall that if we are given two random variables, let us call them x 1 and x 2, then earlier in remark 9 of week 2, we have discussed the fact that even though these random variables may be defined on different probability spaces, we can now construct a new probability space using the ideas of product measures and all that, such that on the new probability space, which is omega tilde f tilde p tilde, we can also construct some new random variables, call them y 1 and y 2, such that they have certain interesting properties that first of all y 1 and y 2 that we are constructing are independent, but we can also say something about the distributions of y 1 and y 2. The first fact is that y 1 must have the same law as x 1, and similarly for y 2 we will say that we can construct y 2 with the property that y 2 and x 2 have the same law. So, therefore, we have these three facts that given any two random variables x 1 and x 2, even if they are defined on different probability spaces, we can now construct a common probability space which we are calling as omega tilde f tilde p tilde. There we can construct new random variables which are having same distributions as x 1 and x 2 respectively, and finally, y 1 and y 2 that we construct are independent. Now, then y 1 and y 2 are now on this new probability space. So, we can talk about certain calculations involving y 1 and y 2. So, let us see. So, in our specific case that we are considering in exercise 7, we are given a random variable x. Now, also consider the other random variable to be minus of x. So, in this case both x as well as minus x are actually given to be defined on the same probability space, but that does not matter, we can still appeal to this construction that we have just recalled. So, we can take x 1 to be x and x 2 to be minus x, and therefore, by this construction we can now construct new random variables, call them y 1 and y 2. So, we are renaming them as y and z respectively. So, in this case y and z are having the property that y has the same distribution as x and z has the same distribution as minus x. Moreover, y and z are independent. So, this is by construction that we have just recalled, and therefore, this was the exercise that we have talked about, that given x, we now consider the two random variables x and minus x, and we can construct new random variables y and z on the same probability space such that y and z are independent and y has the same law as x, z has the same law as minus x. We can show by this construction that phi bar, the conjugate of phi, that is a new characteristic function, and also mod phi square, that is also a new characteristic function. So, this follows from the construction of such y and z that we can construct using the product space ideals. Alright. So, this we have already seen, but let us now consider some further properties of characteristic functions. So, here we recall the fact that one of the necessary conditions for a characteristic function is that at the origin it takes the value 1. Now, the new characteristic functions that we have constructed are out of the existing characteristic function, but we now look at other kind of transformations on the characteristic function which may not give us a new characteristic function. So, this is just by using this necessary condition that we have pointed out, that any characteristic function must take the value 1 at origin. So, for example, if we look at a new function given by a given characteristic function plus 1, then this function new function psi does not have the property that origin it takes the value 1. So, it is not true for the new function psi. So, therefore, we will conclude that the new function cannot be a characteristic function. Similarly, we can look at some kind of scalar multiplications. So, in this situation what we look at is some constant c not equal to 1. So, then multiply this constant with the given characteristic function, then what will happen is that psi, the new function at 0, is taking the value c which is not equal to 1. So, therefore, since this does not satisfy the necessary conditions for being a characteristic function, the new function again cannot be a characteristic function. So, when we are looking at transformations of characteristic functions, we have to be careful. So, typically translations and multiplications by non-1 constants are not going to give us new characteristic functions, but what we immediately have is that the complex conjugate and mod phi square, these operations are giving us new characteristic functions. Alright. Now, we are going to discuss some examples involving the law of large numbers. So, here what we do is that we start with a sequence x n IID and we assume that they are following the distribution normal 0 1, meaning they have mean 0 variance 1. So, in this setting we immediately have, using the independent structure of the x 1 x 2 x n so on, is that the sum of these random variables, the partial sums which we denoted by S n, will have the distribution given by normal with mean 0 variance n, and therefore, we can just rescale it. So, we will get the sample mean which is S n over n, that will have the distribution normal with mean 0, but variance 1 over n. Consequently, if we look at the L2 norm of this random variable, that is just the variance now, because mean is 0, and here this is the second moment again. So, this is now 1 by n, and as n goes to infinity, this goes to 0. So, we conclude that in the L2 sense, the S n over n, the sample mean goes to 0. But L2 convergences imply L1 convergences as well as convergence in probability. So, the sample mean, which is S n over n, converges to 0 in the L1 sense as well as in the sense of convergence in probability. However, we can also appeal to the strong law of large numbers, which we have pointed out certain specific versions in remark 3. So, again by going back to these versions pointed out in remark 3, we will conclude that the sample mean, which is S n over n, now converges in the sense of almost sure convergence to the limit 0. All right. So, we finish our discussion with certain interesting applications of law of large numbers once more. So, we look at something called normal numbers. So, here what we do? We go back to our familiar probability space that we have used multiple times in constructing counter examples. So, here we are looking at omega to be the closed interval 0 to 1 with the Borel sigma field. Now, we can restrict the Lebesgue measure that is defined on the real line to this specific sigma field, and we will end up with a probability measure. So, just for our notational convenience, this restriction will denote by this notation. So, this is a probability measure. Now, if you pick up any irrational number from this interval, it will have a decimal expansion which is non-terminating, right. So, for rational numbers we have terminating decimal expansions, whereas for irrational numbers the decimal expansions are non-terminating. Now, if you fix up some integer between 0 to 9, call it k, then we look at the first n digits of the decimal expansion of this number w that we are looking at. So, and count the number of times k occurs. So, call this number by alpha n k. So, for each omega I look at the decimal expansion, look at the first n digits and find out how many times this number k occurs. So, this number we are just denoting through this notation alpha. Now, let us look at the relative frequency of occurrence of this digit k. So, to do that we have to just look at the alpha divided by n. So, out of the first n many digits, how many times k occurs is alpha n k, and therefore, we just divide by n and we obtain the relative frequency. But suppose I want to look at the whole decimal expansion. So, we let n go to infinity and ask about the limit of these relative frequencies, call this limit to be beta k. Now, we are assuming here that the limit exists. So, if the limit exists, then only we can look at the value beta k, otherwise it is not defined. Now, first let us go back and try to understand the setting. So, we may expect that on average this limit, which is the occurrence of the number k, the relative frequency of that, the limiting value of that is equal to 1 over 10, because we are looking at the numbers k from 0 to 9. So, now consider some number omega to be simply normal if it turns out that this limit exists and turns out to be 1 by 10, meaning it matches with our intuition. So, our intuition suggests that it should be equally likely that all the digits appear with the same kind of probabilities. So, that which is 1 by 10, because we are looking at 10 possible choices from 0 to 9. Now, if it matches with our intuition for some omega, we are going to call it simply normal. But now, let us look at simply normal numbers from the calculations involving law of large numbers. So, what we do is that we first now look at some arbitrary number omega, expand it in the decimal expansion notation. So, the first digit is denoted by xi 1, second digit by xi 2 and so on. Now, here it is immediately clear that the digits are actually giving you certain sequences of random variables, which are IID with the distribution that k occurs with the probability 1 by 10. So, where k varies from 0 to 9. So, this is immediately clear from the outset. Therefore, if we now look at the number of occurrences of k in the first n digits, which we earlier called as alpha n k, this is nothing but this count. So, we will just count for the place j whether the k has appeared or not. So, xi j will be equal to k or not. So, if this happens, we count 1, otherwise we count 0. So, this is what we are doing by this indicator function. So, if you sum them up, we end up having alpha n k, but we have already pointed out that xi j's are IIDs. So, therefore, we essentially have IID sum which is giving you this alpha n k's, and therefore, by our earlier remark on law of large numbers, again we will conclude that this limit must exist and it is going to give us this beta k, and that must be this quantity, which is expected value of this indicator random variable. But expected value of indicator is nothing but probability of the same event, and therefore, this is 1 by 10. So, what we have just proved is that almost surely you will have that for all k from 0 to 9, the beta k is 1 by 10. Therefore, with probability 1, the numbers that we are working with are actually simply normal. So, this is the nice application of the strong law of large numbers, and this is typically referred to as the Bodel's normal number theorem. In fact, you can do the same thing with other expansions. So, here we have used the decimal expansion, but we need not stick to it. We can look at other bases like 2, 3 and so on and expand our numbers. So, again in the rational or irrational numbers, there are all these properties involving the expansion involving other bases, and again we can ask for similar properties. So, for example, if you are expanding in the binary expansion, meaning with the base 2, you are just having a sequence of zeros and ones. So, you can ask whether zeros and ones occur with exact same probabilities or not, and therefore, if it occurs, we will call it normal in the base 2. So, you can now ask more generally whether certain numbers are there which are normal in all possible bases. So, these are all interesting questions which can be dealt with using the law of large numbers arguments. But the idea of normal numbers is very interesting and has seen many interesting developments from other branches of mathematics also. So, we are not going to discuss those in these lectures or in this course, but this is just a quick introduction to the normal numbers that you see as an application of the law of large numbers. Hopefully, this material will make you understand the content of this week better. So, we stop here. Thank you.